All right, here we go again. This next lesson is, I called it's graph parent functions, and all that means, parent, is just the fact that we're going to talk about the most basic versions of a bunch of different functions. I've actually got 7 different functions today, but I'm just starting with the most simple version of it, like the parent, the origin of that function, where it all begins. So it should be pretty easy to follow, real simple math. Let's take a look. I'm going to take you through 7 different functions. Some of them you've seen, some of them you probably have not. All right, so the first one, this is called an exponential function. Exponential. And the reason it's called that is because the variable, the x, the independent variable here, is in the exponent. And this might be one you've never really dealt with. Algebra 1-2 class, I don't think you do. So once again, exponential, it's called that because the x, the part you're going to be plugging numbers into, is up here as an exponent. So whether we know what it looks like or not, as always, it's very easy to figure out. We're just going to make a table. And let's go ahead, why not just put in some negatives, 0, a couple of positives. Always, this is almost always a good place to start, is right here. And then we'll just see what happens. Now, we got a little bit of reminders on how to handle an exponent, so that might stress some of you out here, but let's take it slow. So let's say we plug in -2 into this function. Okay, so we're basically doing f of -2. Well, 3 to the -2 equals, and here's the part you gotta remember. Whenever you have a negative exponent, we really don't know how to handle that. We're supposed to be multiplying 3 -2 times. Well, that doesn't make much sense. But there's a rule that says if we want to turn that into a positive, we just drop it from numerator to denominator. And all of a sudden that changes to a positive. This is definitely stuff you've covered before, but it might have been a while. But a negative exponent, if you want to turn it into a positive, you just drop the whole hunk of stuff from numerator to denominator, like so. And so this is 1/9. And that's what goes right there. And then -1, same thing. 3 to the -1 equals 1 over 3 to the 1, which equals 1/3. So this is 1/3. Here's another rule for you. Anything to the power of 0 is just 1, period. Doesn't matter what number goes here. If it's to the power of 0, the answer is always 1. So that's 1. And the other ones we can do in our head because 3 to the first power is 3, and 3 squared is 9. So this is 3, and this is 9. All right, then of course the main idea here is let's see what that graph would end up looking like. -2 would give us 1/9. So that would look something like, maybe it's going to be tough for me to graph, but give it my best shot. Something like that. Basically -2 and then barely up. 1/9 is a very small number, just barely bigger than 0. And then -1, 1/3 is just a little bit higher than that. These are a little higher than they should be, but it works. And then 0, 1, that's easy to graph. And then you got 1, 3, which would be right here. And then 2, 9. 2, 9 is going to be way up there somewhere, right? 3, 4, 5, 6, 7, 8, 9, something like that. And so this graph ends up looking like this. Now notice that as we go bigger here, it's just going to keep getting bigger and bigger. So that's pretty easy to understand. The bigger look down at the table here. As I make these numbers bigger, these numbers are going to be bigger because we're just 3 to the different bigger powers. So it's going to go crazy big fast. More interesting though is what's happening this way. In other words, as I make x more negative, if I put a -3, a -4, what's going to happen is these fractions keep getting smaller and smaller. It'll be, instead of 1/3, 1/9, it'll be 1/27, and so on. But it's never going to get to 0. There's no number possible that you could put in here that the answer would then be 0 to the whole thing. The only thing you'd even consider would be to plug a 0 in there, but we all know now that 3 to the 0 is 1. So we're never going to get 0. Or in other words, this thing's never going to touch this x-axis right here. It's just going to keep getting closer and closer to it. So there's exponential. This next one will be a little easier to discuss. I'd say a lot easier. This is linear. This is the most simple version, really, of a line. All we need to do real quick is make a table. Okay. And if I put in those same values that we put in for the last one, of course, plugging each number in, it says f of x equals x. That means whatever x I plug in, it's just the answer is the same thing. It's like y equals x. In other words, y and x are going to be the same. So all we do here is we're putting -2, -1, 0, 1, 2. Done. Graph looks like -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc., etc. We just have this line going right through here like this. This particular, and we could put numbers in here. We could have a number here, this slope. We could go +5, and we'd have our y equals mx plus b. They'd all still be lines. If I put a number in front here, or I add or subtract a number, we're still dealing with lines. This is just the parent line. This is like the simplest version of a line before we start shifting it around and putting different numbers in there. It's a 45-degree line. Sometimes you'll hear this called the identity function when it's purely just y equals x. It's called the identity basically because these are identical to each other. They're the same thing. Whatever you plug in here, you'll spit out the same thing. But really just think of it as the nice simple version of y equals mx plus b, where this is 1 and this is 0, the plus 0. Nice and simple. Y-intercept at 0, slope up 1 over 1, creates a nice perfect 45-degree line. All right, next one doesn't have too fancy of a name really. The function has absolute value symbols in it, and so it's called an absolute value function. It has a certain shape to it. We're going to discover it through some quick plotting of points here. So I'll make a table. And why not? Let's just put -2, -1, 0, 1, 2. And absolute value, the actual operation of absolute value means no matter what you plug in here, this makes it positive. It doesn't change it from positive to negative. If you put a negative in here, it becomes positive. If you put a positive in here, it becomes positive. So these answers will be +2, +1, 0, +1, +2. So we have some points to work with, some sample points that we've plugged in, some nice simple ones, and then we just plot them and see what, we really don't need anybody to tell us what all these things look like. I am telling you, but you could discover this on your own as well. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Yep, absolute value functions form a V. So let's make a V. Something like that. Not much else to talk about there. That's it. You got, if it's an absolute value function, you can see that if we want to dig in a little bit here, when you plug in a -2, you get 2, but when you plug in a 2, you get 2. So you're going to get these matching values, and that's what's causing the V, is that you go over here, it goes up, you come over here, it goes up. Well, there you go, you got a V. This next one, obviously we can see here, it's the most simple version of an x squared. It's the first one we've seen today that has squareds in it. We actually talked about this a little bit on the last lesson where we had to plot points, and it was kind of messier than this. This is going to be a nice, simple, what's called a quadratic. Quadratic equations are squared equations. There could be there could be more numbers in here. We could put a number here. We could have plus 3x, minus 2, whatever. But if the highest power of the function is 2, then it's called quadratic, and it has a certain kind of shape to it, which we already talked about. Well, let's do it again. Let's do it from scratch. Make a table. Why not? Go with the same numbers. No reason to stop now. And then we just plug those numbers in. So if we take negative 2 and substitute it in here, we get negative 2 times negative 2. It's negative 2 squared. That's positive 4. If we put a negative 1 in there, it's negative 1 times negative 1, which is positive 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. Kind of similar to the absolute value in the fact that these numbers match and these numbers match. And that has to do, in this case, with when you square something, whether it's positive or negative, it does become positive. You're going to see all these positive numbers here. Kind of like absolute value, only, of course, we are squaring the number, so this number gets bigger. The graph, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Now this one, that almost kind of looks like a V again, but it's a U. It's more of a U shape because it's, as these numbers, if we put a 3 in here, we're going to get 9. So it's going to start going up a lot faster. So it's not going to be this pure straight line thing. It's going to start curving, and then getting the 3, 9 will make it to where it's going up faster than it started going up. So it's a curve. And they always are. All squared equations are U shapes, or we call it parabola. Let's draw it. And try your best to make it look a little curvy if you can. Something like that. And then the actual shape itself is called a parabola. Parabola. The equation is called a quadratic equation, meaning a squared equation, and it creates a shape called a parabola. What's that? This next one's back to not really having much of a fancy name. It's the function itself has a square root in it, and it's called a square root function. This is our first one. We're going to kind of have to change it up a little bit here, because in this one, it's the first one where when I try to make my table, you'll notice that if I just do this, it's not going to work out too well. You can never take the square root of a negative number, because you're asking yourself, let me do a quick reminder here. The square root of, say, 4 is 2. The reason it's 2 is because 2 times 2 equals 4. Whatever's in here, you're looking for the number times itself that would equal that number. Well, two numbers, the same number twice, is never going to be a negative number. So if I tried to plug this in here, it's not going to make any sense. So this is the first time where our domain, or in other words, the numbers we're allowed to plug in to a function, is not including everything. We can't plug those in. So those are done. We'll start with 0. Square root of 0 is 0. Square root of 1 is 1, because 1 times 1 equals 1. But then it gets a little, square root of 2 is a decimal. And we could get out our calculator. In fact, I'll just do it for the fun of it here. It's about 1.4 or so. That's an estimation. But to make my life simple here, I'd rather put in numbers like 4, because the square root of 4 is 2. And then the next number I'd like to plug in might be like a 9, because the square root of 9 is 3. That way I just have the nice clean answers when I'm trying to plot this graph. So now, that should be more than enough. So we can just go over to the graph, 0, 0, 1, 1. I did do 2, 1.4, so why not? So 2 would be somewhere maybe in here. I'm just kind of looking at, this is 1.5 here. I tried to make it a little lower than that. I don't know. It looks close enough. And then 4, 2. So I'm going to actually skip 3 and just go right to 4, and that'll be 2, which is lined up with 2 there. And then 9, so 4, 5, 6, 7, 8, 9, 3. Go up to 3. Now that should be enough to see that this thing is not a line. It's not straight. It's going like this. So square root functions, first of all, they just start at some spot. Like this cannot go over here at all. It's not going to keep going. There's no arrows here because we're not even allowed to plug in these negative numbers into this function to create any kind of value for y. So it just starts right here. This is the lowest number we're allowed to plug in. And then it just kind of goes like this. The higher this number, it will keep going up, but it's kind of going up slowly compared to how it's going this way. So we'll connect the dots. And we've got a square root function. All right, we got 2 more. This one, this is a third power equation. Remember we did squared earlier. That's a quadratic. Third power. This is called x cubed is one way to say that. Instead of x to the third power, x cubed. So this is called a cubic function. That's the fancy name for it. Once again, let's just make a table. We're back to being able to plug in any values we want for x. You're allowed to take a power of any number, whether it's positive or negative. So let's go back to our negative 2, negative 1, 0, 1, 2. And let's just start doing some arithmetic. That's all algebra really is, just a bunch of arithmetic, and then you draw a picture of that arithmetic. So if you take a negative 2, plug it into this function, this cubic function, you're going to do negative 2 times negative 2 times negative 2. That's what third power means. So negative 2 times negative 2 is positive 4. And then 4 times another negative 2 is negative 8. So this is negative 8. Got to get these signs right. Next one is negative 1 times negative 1 times negative 1, which is negative 1. Let's just stop for a second and realize that when you take a negative number and you cube it, it's always going to end up a negative number. Okay, so negative numbers to a third power end up negative because the first 2 negatives multiplied are positive, but then your third one brings you back to negative. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. And 2 times 2 times 2 is 8. Believe it or not, that should be enough to get us going here on what this graph looks like. Not that difficult. Negative 2, negative 8. It's right there. Negative 1, negative 1. 0, 0. 1, 1. 2, 8. Like that. Before I connect the dots, I'll connect them with my laser pointer just so you can see where I'm headed with this. It starts down here, comes up in here. It is curvy. It's going to curve into here, and then it's going to curve again and do that. So try to make the smoothest graph you can here. These are sometimes don't look as pretty as they should. So go like this. Something like that. That's basically what cubic, I call them like a squiggly. They don't really have a name. I mean, I couldn't write you a name here of what this shape is, but it's just like a little squiggle. It's got a little turn to it like that. They're fun. All right, last one. Maybe the trickiest one. I don't know. This is called a rational function. Rational comes from the word ratio. Ratio is a fraction, something over something. So this is a fractional function. Or another way to say it, it's where the x is in the denominator. When the x is in the denominator, we get a whole weird thing going on here. We're going to have a whole unit just focusing on rational functions. And right now I just want to give you just a quick overview, basic idea. Okay? So here we go. No, I want to use, let's use white for that. Boom. All right, I'm going to go back to just the standard -2, -1, 0, 1, 2 again. And real simple math here. It's going to be, you plug in -2, you get -1/2. You plug in -1, you get -1. This is our most interesting moment on this one, right here. You can never divide by 0 in math, ever. Okay? There's no such thing as having a 0 in the denominator. And we can talk about that more, but right now I'm going to stick to the focus of the graphs here. But we just can't do that. You're not allowed to plug that number in. You cannot have a 0 in the denominator. So basically this point does not exist. And then we go back to normal. 1 over 1 is 1, and 1 over 2 is a half. Now if we really want to dig into this, it can get a little heavy. But let's see what we have so far. Okay, we don't have a lot, but let's see. We got -2, -1/2, which would probably be right around there. Then we have -1, -1. And then we're not allowed to even do anything at 0. We're not even allowed to plug 0 in. So along here, right here, there's no graph. So you have to kind of start wondering, like, well, what's going on? What about here? You know, what about over here? What's happening? We'll get to that. But let's skip over it, and then we jump to these other points over here. So we have 1, 1, which is right here, and we have 2, 1/2. Now, I'm going to keep, because this is just a short video, I don't want to get too out of hand here. I'm going to keep it pretty simple, but I'm going to maybe just a little bit more. I want you to understand that, like, what if I plugged in, say, a 10? Okay, if I plug a 10 in there, of course, that would be 1/10. And all I'm trying to do is get you to realize is that the farther I go over this way, like let's say we got over to 10, it's still going to be above this line, but it'll just be barely. It'll be 1/10. 1/10 is a very small number. If I go way over to 100, it's going to be 1 over 100. What's happening here is this graph is getting closer and closer to that line there, to that x-axis, but never hitting it. And that's pretty easy to understand, I think. And the same thing's happening over this way with the negatives. If you plug in -10, you're going to get -1/10. So -10, -1/10, barely, just right below the x-axis there. The part that I'm going to just kind of have you assume for now is that the same concept is also going to happen getting closer to the y-axis here. And that's something we'll talk about more in class as we get there. We do some more homework problems. But same concept, just a little more arithmetic to do to explain it. But that's what a rational function looks like. It's always going to be at least 2 parts to it, because there's always, when you have a rational function, there's always going to be something, in this case just a pure 0, that's bad. And whatever that bad thing is, well, the graph can't exist there, so you kind of breaks it up. It's, we have this, we're cruising along, we got a graph. Oh man, I'm not even allowed to plug in that number. All right, well, whatever, skip over that and then start over, and you get another piece of graph over here. So that's it. This lesson is on parent functions, meaning the basic versions of lots of different equations, which lead to different types of tables, which then lead to different shapes of graphs. All algebra really is equations, tables, and graphs. That's really all there is ever. And we just saw 7 different kinds. Work hard, be nice, see you soon.